Today we are going to discuss about Schmitt Trigger. So here is the basic circuit of this Schmitt Trigger. We are going to use it in our laboratory. The circuit diagram. So where the basic information about the Schmitt Trigger is like this. Also it is called as a regenerative square unit. So first let us see what it is ST means. That means Schmitt Trigger. It is a regenerative comparator. It converts sinusoidal input into a square wave output. The output of the ST swings at upper and lower threshold voltages, which are the reference voltages of the input waveform. Okay, let us see some of the difference between the comparator and Schmitt trigger. So comparator compares with fixed reference, whereas the Schmitt trigger compares at the different references called UTP and LTP. So there are two types of feedback in Schmitt trigger. One is positive feedback, another is the negative feedback Schmitt triggers available. The main applications of the Schmitt trigger is interfacing signals between the analog electronics and digital electronics and translating levels within different logic families. One major problem encountered during this process is the pickup of noise. Digital signals are coherently fast because they deal with the high frequency and fast rising and falling edges, whereas in the analog the change at the mixed slower pace in terms of the rise and fall times. To tackle these problems, Schmitt trigger is used using operational amplifiers. Schmitt trigger is a comparator circuit with a hysteresis implementation by applying positive feedback to the non-inverting input of a comparator or differential amplifier. It is an active circuit which converts an analog signal to the digital output signal. Why it is called as a Schmitt trigger? The Schmitt trigger, the trigger is the name. Schmitt trigger comes from the fact that the output retains its value until the input varies sufficiently the trigger a change. So let us see how to assemble this circuit and to get the output straight away without any mistakes. So here, as I explained, that the Schmitt trigger working principle is to convert a sinusoidal waveform into square waveforms. So this is the schematic diagram of the practically we are going to use it. So next to this you can see that there is a pictorial diagram here. This pictorial diagram is nothing but arrangement of the components on the breadboard as well as the other instruments like power supply, function generator, CRO and all these things. It should be like this. See, the 90K resistor is connected between 6 and pin number 3. So you can connect between pin and 6 like this, and from pin number 3 a 10K resistor is connected, and to a single port parcel as a reference voltage where it is connected is the positive terminal and the negative terminal is connected to the ground. This is what the arrangement you have to do. After this, let us see what happens and what kind of waveforms we are going to get in the next slide. Now you can see that let us see, say once you connect all this, switch on the power supply for 10 volts peak to peak, signal generator 10 volts peak to peak, and expect that the square waveform as an output. So on the CRO it looks like this. So first channel you select always the output. This is very important because we have to trigger both the signals and we have to get a stable waveform. And the second channel you connect it to the input of the function generator so that you can compare both the waveforms like this. Now you can see that there is a rising edge and a falling edge here. So you have to move this waveform. This is explained practically in a video, but I am going to explain this theoretically. It is using a sheet. Here this is a rising edge and this is falling edge. See that the falling edge which touches the input signals at the peak of the positive half cycle of the input signal. So that is called as a UTP. Whereas the rising edge of the output waveform is, just you move these waveforms and you can see that it is the lower part of the positive half cycle, it is touching the edge of this. So this is called as an LTP. So calculating this, you can find out at what UTP and LTP with the reference voltage of 3.3 volts. In our laboratory we have done that, the reference voltage is 3.3. It is actually both the threshold points are positive half cycle of the input signal. This is what called reference voltages. Here practically it is called as a plus 4 voltage and this is minus 2 voltage, sorry, plus 2 voltage, because both are plus and you are going to see this as an output. This is clearly explained in a video attached to this same experiment, and you can see that one more waveform. This is one more method where you can measure the LTP and UTP. Just press the XY key after displaying both the keys, press the ground key and bring it to a common point, then release that ground connect. Then you see that you can observe a waveform something like this, is called as a hysteresis loop. Here also you can measure that LTP and UTP. So with respect to this x-axis, the coincident of the x and y plots, you can measure the distance here. This is the nearest point of this, shows us the LTP. So LTP, it is the whole waveform is moving completely in between first and second quadrant, so which shows that it is positive. So when the distance between this point is called a plus 2 voltage and the extreme end, say till this point, it is a 4 division. Actually you will get practically 2 divisions into multiplied with 2 volts per division, actually 4 volts. So both UTP and LTP are on positive side, that is 2, that's why it is called as a positive, and this can be shifted on left side also, or in between, one is positive, another negative. It is possible by design and reference voltage variations. Thank you. This is what called LTP, where you have to measure from the ground. It is 1 division, and you can see that it is the volts per division is the input voltage. Actually you would say that it is 2 volts. So 2 into 1, it is 2 volts. That is on positive side of the cycle it is there. So it is exactly like this. Position this. So it is plus 2 volts. Now let us say the UTP. Say it occupies 2 divisions here. So 2 into another, here the volts per division reading is 2 volts. So plus 2. Both the LTP and UTP are both on positive side. That's why LTP is plus 2 volts, UTP is plus 4 volts. Okay, now let us say that measurement of the LTP and UTP using hysteresis loop. What you have to do for this, display both the waveforms and select XY key here. Okay, press this. First you may get that a horizontal diagonal line, something like this. Release it. Once again you press it 1 or 2 times, you will get the hysteresis loop. Now to set this, before taking this reading, you have to press ground keys, both the channels, and position it exactly on the center of the y-axis and x-axis cross section. Position it like this and release both the keys, and see that here it is completely shifted towards the between first and second quadrant. So both are on positive side because our design is plus 2 volts and minus 2. Here you can see that there is a 1 division here for LTP and there are 2 divisions for this for UTP. So that means 1 into 2 volts, and 2 into 2 with respect to this volts per division reading, it is plus 2 volts. So this is another way of displaying LTP and UTP. Thank you.